Greetings everyone, this is Jeff Wilkerson, Professor of Physics at Luther College. Today we're solving a circuit analysis problem that we started this morning in Physics and Engineering, Introduction to Physics and Engineering Science here at Luther College. And so this is for the problem the students were working on the board. We have here 12-volt battery, 5 ohms, 3-volt battery, 10-ohm resistor, 5-ohm resistor, and a 9-volt battery. So we're going to apply Kirchoff's rules to this problem and see what we can do. First of all, we have to assume a direction that we think the current is flowing in each branch. We're going to take I1 and have it flowing this direction. It's going to come out of here. So I1, current can only change at a junction. So from here to here to here will be I1. We're going to assume I3 is flowing this direction in the middle, and I2 is flowing this direction in the bottom half. Where these things meet, we have I3 coming together, we have I2 coming together, and I1 coming out. So I1 is equal to I2 plus I3, the way we have written it. So that's our junction rule, gives us that equation. Then we do a loop rule, and so we're going to walk around. We'll start here and walk around the loop and the top up here. That'll be our first loop. So we're going in the direction of I1. So going in the direction, the assumed direction of I1. If we get the direction wrong, remember, we'll get a negative current, and that'll just tell us to swap this direction around. So in this direction of I1, we get minus I1 times 5 ohms as we step across this first resistor. Then we're going up the battery from the negative side to the positive side, so it's plus 12 volts. And then we come on around here, and we're going in the assumed direction of I3, so it's going to be minus I3 times 10 ohms, and we go from the low side of this battery to the high side of this battery, plus 3 volts is equal to 0. So that's our first loop. We got the sum of the potential changes around the loop is equal to 0. So now we're going to do loop 2. Loop 2, we'll start here and loop all the way around. So we're going in the assumed direction of I2, minus I2 times 5 ohms. Is that potential difference. We go from the low side of the 9-volt battery to the high side of the 9-volt battery, gives us 9 volts. But now we're up here, we're going from the high side of the 3-volt battery to the low side of the 3-volt battery. So that's minus 3 volts. And then we've got, we're going against the assumed direction of I3, so that's going to be plus I3 times 10 ohms is equal to 0. So that's our two loop equations. We got our junction equation, we got two loop equations. We could have done a loop around the entire outside. We just picked these two loops to do. We add these two loops together, or subtract these two loops. Take this loop equation minus this loop equation is going to be minus I1 plus I2 times 5 ohms. And then we've got 12 volts minus 9 volts is 3 volts. And 3 volts minus 3 volts is 6 volts, so there's 9 volts from the batteries. And then we've got minus 2 I3 times 10 ohms. So we got minus I3 times 10 ohms is equal to 0. Remember what we're trying to find here was what the current is, the direction of the current. We assumed the current was left to right, so if we get a positive answer, we'll be left to right. And we want to find the magnitude of the current in that resistor, in that branch, in the middle branch right there. So we've got this, but we know that we can solve this equation for minus I1. Let's move I1 to this side and I3 to this side, and we see that minus I1 plus I2 is actually equal to minus I3. So we can stick minus I3 in there. We've got minus I3 times 5 ohms plus 9 volts. Minus 2 I3 times 10 ohms is equal to 0. And we pull that together. We got I3 times, move these two things over to the other side. And we've got I3 times 20 ohms, pull that 2 inside right there, plus I3 times 5 ohms is equal to 9 volts. Or I3 is equal to 9 volts divided by 25 ohms. When we combine those things together, I get 0.36 amps. That's not what the book said it was when we looked at it this morning, but that's what I get is 0.36 amps left to right. So that's what we're looking for. That's the solution to the problem we were working. We might ask the problem, what's the rate of energy dissipation in this resistor, or what's the power in this resistor? And now we know the current in that resistor. If we know the current in a resistor, the easiest way, we say the power is equal to I times V. But V is the potential, I is the current through that resistor, V is the potential across that resistor, and so I times V, V is equal to IR, as Ohm's law, is going to be equal to I squared R. And so we've got 0.36 amps squared times 10 ohms, and that's going to give us a power dissipation in that resistor of it looks to me like 1.3 watts. So does that look, yeah, that looks about right, I guess. 1.3 watts would be the power dissipation in there. Well, that wasn't the question that we asked this morning, but we could easily ask that question. So that's what we got. That's how we did the circuit analysis here to find the current in that middle branch, the current in the 10 ohm resistor. So thanks for watching, everybody.